In this lecture, we're going to talk about section 18.6, which is electric field and energy. Um, we've discussed up to this point, particularly in the previous chapters, the concept of energy. Um, it's the ability to do work, and we have to keep that general conception of energy going forward. Now, we've done it for mechanics. So how does that apply to electricity or electric potential? So we need a way to model this, and that's what this section is going to try to describe. So the energy, and it's going to be represented with U, just like it has been before, required to charge a capacitor C to a particular potential difference at a charge Q is equal to the energy stored in the capacitor. And it probably doesn't surprise you too much. Now, the formula is going to be given by formula 18.19 here, which is going to be the energy is equal to the total amount of work that it takes in order to be able to make this situation happen. And you can see here, it's going to be the voltage divided by 2 times the charge. And then when you remember here that the voltage is going to be the charge divided by the capacitor, capacitance, then you can see the replacement there. And then in rearranging this, you can also see how it's going to be 1/2 C times the voltage squared, which basically if you take Q over C, you have that squared, you'll have to add an extra C in here in order to be able to make that work. So this energy can be thought of as residing in the electric field between the conductors. Now the energy density U is going to be given by 1/2 times the vacuum permittivity times the electric field squared. So let's take a look at the section here and let's kind of see how they describe this. Okay. The many of the most important applications are going to be of capacitors depend on their ability to store energy for later use. The capacitor plates with opposite charges separated and attracted towards each other. They're very analogous to a stretched spring or an object lifted in the Earth's gravitational field. The potential energy corresponds to the energy input required to charge the capacitor and to the work done by the electric forces when it discharges. That's analogous to the work done by a spring or the Earth's gravity when the system returns from its displaced position to the reference position. So basically what you're doing is you're storing energy in all of these particular cases. So how do we calculate it? We're going to take the work that's required to create it, and that's going to give us the value of the potential energy. So the final charge Q and the final potential difference going to be related by this formula. I don't think that surprises anyone. So let V and Q be the varying potential difference and charge, respectively, during the charging process. At any instance, then the voltage is going to be equal to the charge divided by the capacitance. The change in work required to transfer an additional small element of charge Q is going to be given by this. In other words, the change in work is going to be the voltage times the change in the charge. That voltage, again, is going to be Q divided by the capacitance. The work needed to add that extra charge increases in direct proportion to the amount of charge Q already present. That shouldn't surprise you because the amount of charge there has to be factored into how much more charge you can add in. We all know that the like charges are going to repel. So there is an effect there that has to be modeled. So the potential difference is already created. The total work done needed to increase that charge from 0 to a final value of Q is going to be the average potential difference between the two. So when we take the Q here, and we're going to keep that there, and we're basically going to replace this with the average potential that it takes in order for us to get from there to there. From the Q to the from the original Q up added adding the extra charge in there. So when we do that, we realize what the voltage is equal to, which is Q divided by C. Place that in there, and then we can rewrite that into this formula, just like we saw in the summary. Units are going to be joules. V again is going to be the potential difference or the voltage across the capacitors, and Q is the magnitude of the charge on its plates in coulombs. And you can see here that this does not depend on Q or V. So if we define the potential energy of an uncharged capacitor to be 0, that's not unreasonable, then the work total is going to be equal to the potential energy of the charged capacitor. When Q is in coulombs, C is in farads or coulombs per volt, and V is in volts or joules per coulomb, this ends up being in joules, the potential energy, that is. So the charged capacitor, again, is the electric analog to a stretched spring with elastic potential energy, U is equal to 1/2 kx squared. The charge Q is analogous to the elongation, in other words, the distance that you separate from the equilibrium position for the spring. And it is going to be the reciprocal of the capacitance, or the reciprocal of the capacitance is going to be the analog to the force constant K. The energy supplied to the capacitor in the charging process is going to be analogous to the work we do on the spring when we stretch it. So what about the energy density? The energy stored in a capacitor is related directly to the electric field between the capacitor plates. That shouldn't surprise you. We can think of the energy as stored in the field in the region between the plates. Now, to develop this, we're going to find the energy per unit volume in the space between the plates of the capacitor. Those plates are going to have an area of A, which we've seen before, and a separation of D. And we're going to call this quantity the energy density, and we're going to denote it by U. We know what the total potential energy is, and we know the volume is basically the area times the distance of separation. So the energy density is going to be the volume, or the energy divided by the volume. If we go back and look at equation 1816, we can see the capacitance is defined by this. Potential difference is related to the electric field magnitude with this. Once you substitute both of those into here, this is the formula that we come up with. Now, we went through this thinking of only one specific kind of capacitor, but as it turns out, it's valid for any capacitor in vacuum or for any electric field configuration in vacuum. We think of a vacuum as a space with no matter in it, but vacuums actually can have electric fields and therefore energy. In other words, it's not just empty space, which can kind of throw you for a loop there, but that's what we see.